I am Yash Nahar, and I'm here to present my final project for the deep learning course, Object Detection for an Autonomous Driving Car using Yolo. For self-driving cars to be able to perceive their surroundings very accurately and precisely, it is necessary that they do it with limited human intervention, and they should be able to interact with the real-time stimuli on the streets. Hence, I chose this topic, and which allows me not just to learn a deep learning model, but to look into this very exciting field of self-driving cars and how they perceive their surroundings and perform object detection. Having said that, I have chosen the famous Yolo state-of-the-art object detection model, which is very good at performing object detection in complex scenes at very high accuracy and fast processing speeds. So today I will go through the entire work that I did for this project work, where we will first touch upon the what is YOLO, its architecture, and why YOLO V5 I chosen specifically, the data sets, and then step by step through the software requirements, setting up the software packages, the model architecture, and then the regular machine learning workflow, where having set the model architecture, we go through training the model, evaluating its performance on the train and validation sets, testing it, looking at the results and visualizations. Finally, drawing inferences out of the steps performed above, and then summarizing the challenges. Of course, while training deep learning models, there are a lot of challenges that we faced, the solutions and the lessons that were learned. And I have also documented some future scope for this project work, deep learning being a very deep and extensive field. A lot more can be done, but I have limited some of this to the scope of this project. And then I have attached the references and the YouTube URLs. So, having already told you what the motivation was behind choosing this problem statement and why YOLO 5, let's look at a little bit in detail about YOLO. So you only look once. It's an object detection framework. It's framed as a regression problem and allows us to spatially separate the bounding box and the associated class probabilities. It works in 4 steps basically: uh, building residual blocks, bounding the box regressions, intersecting over unions, and then doing non-maximum suppression. So it's resizing your image, running the single convolutional network, and then performing non-max suppression in a nutshell. So YOLO V5 specifically, it's also a single neural network object detection model. It uses CNNs to predict bounding boxes and class probabilities, but it is an improved version of the previous YOLO V1 to V4, and it's again set up as a regression problem. But the network design is much more efficient. It has improved training techniques, thus leading to a better accuracy, better speed up, and its ability to perform in more complex data sets. So that's here. I've put on some numbers. It's 88% smaller than the YOLO V4 and 180% faster, and roughly similar accuracy. There is one cons, of course. I will not. It's a soft con. Maybe there was no official paper released like other YOLO versions, so it's still under development, and there are frequent updates received from Ultralytics. So we have to be careful to look at the latest update for bug fixes, if any. But it's fairly stable. Okay, now coming to the data set. I have used the autonomous driving car data set from RoboFlow. So RoboFlow basically has a large repository of open and public data sets, especially for object detection. And they help you in no time customize it depending on the platform you are training it on. So this self-driving car data set that I have used has roughly 97K labels, 11 classes, 15,000 images. I have used all 512 by 512 images, of course. The download instructions are generated by RoboFlow. All you need is an API key. It's easy to obtain. So let me just quickly show you how you can. So this is the RoboFlow website. You can choose which kind of model you are training and what is the platform. And based on that, it is going to give you the download instructions. API key generation is very easy. Go to its settings page and generate your API. And it gives you a code which looks like this. And then, of course, it puts all the images and labels in a single is folder, so you need to split it using split folders. You may choose to do so with some other tool that you feel fit, but split folders is a very quick and easy way to split your images and labels into train, test, and validation sets. So this is about the data set. Software requirements, a good GPU and decent RAM is necessary. I have used Google Colab Pro. The GPU speed up ensured that every model I trained did not take more than, let's say, 5 hours. A normal my current Mac M1 or a Google Colab without the Pro did not seem to do it as fast. It would have taken more than 8 to 9 hours for a single model. So the libraries, of course, major libraries used are PyTorch, Matplotlib, Seaborn, split folders. Algorithm is Yolo v5. This is the repository. And the requirements.txt in the Yolo v5 GitHub repository is sufficient to get all your software requirements set up. I will be going through the architecture setup in detail via the Google Colab notebook as well. But in a nutshell, I have performed 3 different model trainings. First one is using the YOLO v5 architecture as it is, as defined in the YAML file, and training it on the customized self-driving car dataset. Then I attempt to tweak the model by adding 2 more layer sets in the middle. As you can see here, they are highlighted in bold, adding a convolutional layer, the unsample, and the concat at 2 levels right in the middle and observing its impact on performance. And finally, there is something called as evolution, which allows us to do automated hyperparameter tuning with YOLO V5. That is what I have attempted in the third iteration of model training. Model training is simple. We will have a detailed look at it, but we have to use the train.py and pass all the parameters correctly to begin the training. So let's switch to the Jupyter notebook as to how to set all of this up. So those of you who might be interested in the YOLO original paper, it's a very interesting and an extensive paper. It gives some very good insights into how the architecture was built and why is it performing so well. Please go through this. arxiv.org, ARXIV has a very good, it has a free PDF available. It tells you the architecture, the introduction, good visualizations, how it looks at creating a grid for forming the class probability map and the bounding boxes plus confidence at once, and finally doing the detections. And the math around it has also been explained very well. So I will not get into the details of the paper with the limitations of the time we have. Let's straight jump into the notebook. So as I said, Google Colab Pro, you need to set up your GPU. Let me quickly show you how to do that. So once you come to your new notebook, make sure that you go to runtime, change runtime type, select the hardware accelerator as GPU, the GPU class is premium, and then run type as a high RAM. Now what this is going to ensure is it's going to give you either a V100 or a A100 NVIDIA GPU and a high RAM to make sure that you make the most of your Google Colab Pro subscription and thus get very quick model training. So this is the notebook, right? And first is a sanity check to look if the GPU has been loaded correctly. So this ensures that GPU, the RAM is good, 89.6 GB. This varies depending on at what time of the day you are running. I have mounted my Google Drive. This ensures that even if we, stop at some point, when we come back, we don't have to perform all steps again. Decent space in Google Drive helps to restart where we left. Having mounted the Google Drive, I have cloned the YOLO v5 repository from Ultratech's GitHub. As I've already described, install the requirements using requirements.txt, perform all the imports, And then finally install RoboFlow Python package, and then use the small code snippet that they gave us to download the data set with the API key, of course. Having downloaded the data set, we have a look at the data.yaml file, which gives us the class structure, the number of classes. As I said, this is the YAML file which is describing the original Yolo v5 architecture as it stands. In the first run, I am using the architecture as it is, with all of the convolutional layer as it is, the backbone and the head as it is. So while I'm doing a write template, it is just a copy of the exact Yolo v5 YAML. In the subsequent iterations, we will modify it. So having done that, as I said, we split the folders and make sure we have train, test, and validation sets. Split folders make something called as val. We have to manually change it to valid, and then finally perform the training. I first performed the training on 5 epochs and did all the tensor board performance and visualization testing on 5 epochs. And then once I was sure that everything is set up well, I have done it for 50 epochs. So as you can see here, I have said performing some predictions on the 5 epochs itself, but here is where I start with the 50 epochs. So it takes roughly about, I think, 2 hours it's roughly around 3 hours, but it keeps showing you the performance after every epoch. It is showing you the summary after end of all epochs and showing you the class-wise summary of your performance metrics. And then we look at the train and validation performances. So as you can see, consistently the train box loss, object loss, class loss for train and validation sets decreases over time. It plateaus after around 25 epochs, but still steadily decreases. Precision steadily increases. A small drop has been observed at 40 epochs, and recall also steadily increases. So overall, good performance. At the end, we come to roughly around 79-80% accuracy and a 60% of recall at the end of 50 epochs. You can of course look at other performance metrics. So having done that, then I have looked at the training data as to how the object detection was performed on the data it was trained on. Naturally, it is doing very well, being able to perceive all of the images correctly, and not just perceive them, but classify them into the right classification types. So with that, I have done testing on the test data set, and then randomly looking at certain test data sets. If it is able to perform the predictions correctly, it seems to be doing a good job. Finally, to do some true out of sample testing, I have made sure that I upload 5 images of my choice from Google, random traffic images, and test the train model on those 5 images. So overall, again, it seems to be doing well, looking at cars, pedestrians, but when a seriously different image has been given to it sort of uh, is able to look at objects which are very close to it, but it is failing when it sees too many objects a little away from it. So I think this is an anomaly and will need training on a diverse and a very specific data set when it comes to high traffic countries. So after that, I have performed hyperparameter tuning using evolution. Evolution by default performs 300 evolutions for, let's say, if you've done 25 epochs, performing for 25 into 300 would be very time consuming. So I have restricted it to 2 evolutions just to demonstrate the idea of evolution and observe the performance impact. I have also tried to modify the architecture as mentioned in the PowerPoint presentation by adding 2 layers in the middle and observe the performance impact. I will not go through the steps in detail because they are similar to what we looked at the first notebook. So Again, I've done it for 25 epochs only because it has been time consuming. So, but 25 epochs is decent to understand the impact on performance and compare it vis-a-vis how it was when it was 25 for the original architecture. So, with both of these performed, let me quickly give you a gist of how the performance has impact has been observed. So if you look at the modified architecture, it is realized that in the train and the validation sets, a lower loss has been observed. So which means the loss has reduced, the precision and recall has improved modestly. Even with the evolution, just with two evolutions, there is a very modest impact in performance, but it is uh, very indicative of the fact that if we were to perform evolution for the larger data sets with more evolutions, with more epochs, it will definitely lead to a good. Of course, it's going to come at a cost of time and resource, but it's a trade-off analysis that one has to consider while making that decision. So this is the class-wise performance. So it's good across the classes. At some classes which are underrepresented, naturally, you will find that it is not doing exactly as we expect it to do. So quickly coming back to, summarizing the inferences, YOLO is a very robust architecture. V5 is performing well on customized data sets, especially on the autonomous driving cars, and 25 to 30 epochs is decent for training. Modifying the architecture did have a modest impact, but I think we need overwhelming evidence and very strong testing on different data sets for more epochs to make some, warrant an actual change. Evolution definitely for highly meticulous tasks like autonomous car driving, it is, I think, warranted that that kind of time and resource can be spent to achieve greater accuracy and more speed. Some challenges, Google Colab was slow, so high GPU and RAM was necessary. So it did cost me $100, but an improvement was observed in the speed. Out of sample data, high traffic images from India did not yield very good results. But again, indicative that for country specific, for autonomous cars, models will have to be trained very regional specific data to account for factors like regional density, population, terrain, volume of traffic, etc., modes of transport use, etc. So summarizing the future scope, I think version 7 is also there. It will definitely be good to look at the comparison with V7. Other state of the models like vision transformers and beyond them can be used. Hugging Face is a good example. A trade-off analysis of hyperparameter tuning versus time and resource and the cost benefit would be a good indicator for business adoption. Augmentation of the training data set to improve performance is another future scope. And of course, looking at different data sets in diversity and volume would lead to better understanding of these. At the conclusion, I would like to thank Ultratix. Most of my references have been from Ultratix on their tutorials for training custom data sets, the best tips for training, and their hyperparameter evolution and RoboFlow, of course. Thank you, and I hope this tutorial has been